So let's talk about multiple linear regression. Multiple linear regression is an analysis technique that is useful if one wants to test hypotheses regarding one and not more than one continuous dependent variable and two or more independent variables. So now that we know when we can use multiple linear regression, let's take a look at how to do it. Before we can actually carry out the regression analysis, we should first check whether the data complies with the number of model assumptions that are required by a multiple linear regression. And those are that there's a minimum sample size. Multiple linear regression can only be applied if there are 10 to 30 observations, that is cases or responses, for each independent variable. Secondly, the dependent variable should be measured at interval or ratio level and should be normally distributed. Furthermore, the relations between the independent and dependent variables should be linear. Fourth, for any pair of observations, error terms, that is the difference between the measured and the model values of variables, should be uncorrelated. And the variance of the error terms of predictors should be constant, that is homoscedasticity. Furthermore, there should be absence of multicollinearity, that is, none of the independent variables should be correlated with any other independent variable. And finally, errors should be normally distributed. So let's now take a look at how we can check these model assumptions. So in the dataset, there are 120 cases for 3 independent variables. So sample size, we are quite fine with that. So let's look at another model assumption, that is the normally distributed dependent variable. We can graphically inspect it. So we can, its turnover intention, and we can make a plot of it and make a histogram. And if we do it, again, turnover intention is the dependent variable, we can see it is by and large normally distributed. However, we cannot really test it by graphical inspection. There is, however, a measure which we can use. And it is called the Shapiro-Wilk test. And the Shapiro-Wilk test has a value of 1 if the variable is perfectly normally distributed. And if it is significantly smaller than 1, the distribution of the variable under study is not normally distributed. So basically, we are looking for a non-significant test of the Shapiro-Wilk in order for the condition of normality to be met. And we can look at it here. It says a 0.084 level of significance. That's not significant, so we are fine here. Okay, so now let's take a look at multicollinearity. We can do it in 2 ways. We can look at a table with the bivariate correlations or a correlation matrix, and we look whether all correlations between independent variables are between minus 0.7 and 0.7. So we choose Analyze, Correlate Bivariate, select them, and we see that, well, it's pretty much all right. What we can also do is to correlate the variance inflation factor. it measures the correlation between the various independent variables. And in SPSS we choose analyzed and regression, then choose any dependent and the independent in the various boxes. And under statistics, choose collinearity statistics. And then you'll see that the VIF values are reported. And if they are below 10 or even below 4 by convention, we are safe. Okay, so let's check linearity. We do that in a graphical way. So we can look at a plot with standardized residuals on the y-axis and standardized predicted values on the x-axis. So we do it by analyze, regression, and linear. And we select the appropriate dependent and independent variables. And in plots, we check and choose Z residual and Z predicted. And then a plot is produced. And generally, if the values are dispersed with a relatively random pattern, which is the case here, we assume there are linear relations. So that's good. Okay, let's check for absence of autocorrelation. We can make a plot of it, but the most popular statistical test is to detect autocorrelation is the Durbin-Watson test. It's a test of linearity of error terms, and the rule of thumb is that a Durbin-Watson between 1.5 and 2.5 signals absence of autocorrelation. And we can produce the Durbin-Watson here under Analyze, Regression, Linear, and then the Statistics dialog box under Residuals. And we see an example that the Durbin-Watson is 1.955, which is, again, perfectly fine. So finally, let's check homoscedasticity. The error terms of the predictors should be constant. We can check this again with a plot of the, in this case, Z residual on the y-axis and the Z predicted on the x-axis. So analyze, regression, linear, select dependent, independent, and then check the dependent on the y-axis and the Z residual on the x-axis. And if the distance between the dots and the diagonal stays roughly the same, no bowing outward or inward, there is indication for homoscedasticity. In the example, there is no bowing, so we assume homoscedasticity. So now that we have checked all model assumptions, we can actually carry out the regression analysis. We do that by choosing the appropriate dependent variable, which is turnover of intention, and the independence. We choose model fit and R-squared diagnostics and carry out the analysis. And then we look first at whether the whole model is a fit by looking at the ANOVA, and then at the beta values and the significance levels. And then we can see that two of the independents have a significant impact on the dependent and one does not. So with this information, we can actually test the hypothesis. The take-home message for this one is that in order to carry out a multiple linear regression, before you can actually carry out the regression, you have to do a lot of checking of model assumptions. And there may be issues with them. Sometimes you can repair it, sometimes not. First and foremost, it is of crucial importance to always report your assumptions so that the interested reader can check how to interpret your findings and whether there are alternative interpretations.